Peter. So today we are happy to continue our series lectures on literature and history on mathematical science as a joint effort between CMSA in Harvard and also YMSC in Tsinghua University. So today we have the speaker, Professor Kenji Fukaya, and Peter Kroheimer will be the chair for this whole talk. Peter.
Thank you, Yao. So welcome to today's talk in this excellent series we've been continuing for a while now from CMSA. Just before I introduce the speaker and we begin, let me remind you that in this webinar format on Zoom, you can ask questions through the Q&A, which is different from the chat down there, and is probably the better method to post questions, which Kenji will perhaps try and answer at the end of the talk. There'll be time for discussion at the end. But do post your questions perhaps as we go along if you have them. So I'm very pleased to introduce Kenji Fukaya. He has, over many years, made important contributions to global Riemannian geometry, the foundations of instanton Floer homology, and his ideas have been seminal in symplectic topology and Floer homology of Lagrangian intersections. His visions have guided research in these areas for many years, and today he's going to talk to us with an overview of homological and homotopical algebra and modular spaces in topological field theories. So from the Simon Center, welcome Kenji Fukaya. Thank you very much.
Thank you for introductions. So I want to share screen. Okay, yeah. So something I want to talk is this three kinds of things: homological algebra, moduli spaces, and topological field theories. And the story of this kind of thing starts in 1980s. It's something like 40 years ago. And the story starts somehow the counting the number of solutions of certain nonlinear partial differential equations, and people found that this gives some interesting invariant in Heuris areas. And one most first thing is this Simon Donaldson, who found that this kind of numbers of solutions of AST equations on four manifold is a very interesting invariant in a smooth four manifold. So this is an AST equations. A is a connection of some vector bundle on four manifold, typically SU2 or SO3 vector bundles. And this is FA is a curvature, and you have this Hodge star. So this is anti-self dual equations. And slightly after that, Gromov found that for a symplectic manifold, you put some compatible almost complex structures, and you consider map U from Riemann surface to a symplectic manifold, which is holomorphic, satisfy this equation. And this equation is called nonlinear Cauchy-Riemann equations. And Gromov found that counting number of solutions of this nonlinear Cauchy-Riemann equation is a very important invariant of symplectic manifold. So this is in the 90s. And in these both works, there are some features. So usually, we need to take some auxiliary choices to define equations. So in this Donaldson's work, we start this XX4. This is a smooth four manifold. But then we need to fix some metrics, Riemannian metric, or at least conformal structure, so that we have this Hodge star operator. So once we fix this Hodge star operator, we can write down this anti-self dual equations, and one can start counting the solutions. And in this world of symplectic geometry, so we start from symplectic manifold X omega. So omega is a two form, which is closed. And omega to the power n became non-zero, nowhere zero. So this is a symplectic form. And then we need to check J. J is an almost complex structure. So J is from tangent boundary to itself, so that J square is -1. And important is that omega JB, JW is omega BW, and omega BJB is positive. So under these assumptions, we can just consider this Cauchy-Riemann equations. This means that d by u equals 0 is equivalent, that this differential from Riemann surface, tangent boundary of Riemann surface, the tangent boundary of x, this is j, this is √-1. This is a complex linear. So to write down this equation, you need some extra choices. And the important feature is that the solution set itself. So you consider this kind of equations or this kind of equations. The set of solution itself may depend on the choices like star or j. But if you count the number with sign, then it is invariant, independent of the choices. So that's somewhat similar to this intersection number. So you consider these intersections between this red line and the black line. Then in this picture, you have 3 intersections. But in this world of this dual geometry, you have this sign count. So this is plus and this is minus, this is plus. So you move this red line a bit, then you have only 1 thing, but this one is a kind of 2 plus and 1 minus. So it's 1, and this is also 1. So this is the kind of story. So the solution set itself depends on the choices, but the number counted with sign is independent. And this is the kind of what this topological field theory means. And I think this word of topological field theory is invented later on by Edward Witten. And in the physics language, kind of, I'm sorry. Yeah, so this kind of phenomenon happens not for all nonlinear PDE. So there are a lot of interesting geometric PDE appearing in geometric analysis, but this kind of counting makes sense only in some rather small number of cases. So if, for example, if you consider this 4 manifold cases and gauge theory case, anti-solution equation on 4 manifold, you count it, it's a good invariant. But you have this Yang-Mills equation. So the Yang-Mills equation is something like this, this Yang-Mills functions. This one is 0. And the ASD equation is somehow a special case of Yang-Mills equations. But to count the number of Yang-Mills equation does not make sense in this way. And in a similar way, the number of nonlinear Cauchy equation, that this equation d bar u equals 0, this number is a well-defined meaning, but holomorphic map is a harmonic map, but if you try to just count the number of harmonic map, that's not a good number. So there are some special feature so that we can get this kind of things invariant in this way. And I think physicist interpretation of this phenomenon is the following things. So they usually count this kind of integrals, like this configuration space. In the case of Yang-Mills, it is something like a space of all connections. And in the case of holomorphic curve, it is a space of all maps from sigma to x plus some space of all almost complex structure, all complex structure on a sigma. Then they have this kind of some integrals, path integral, and they integrate some things. And there are some miracles, something which they call supersymmetry. And these integrations end up with some integrations over some spaces. And this space M is a set of a critical point of this functional we put on. And this critical point means that usually this M is a solution set of certain nonlinear PDE. So this picture says that why this kind of number is a well-defined invariant. So for some particular nonlinear PDE, you have this kind of pictures so that you get well-defined numbers. And in various cases, this number is very much interesting, invariant. So that is a story started in 1980s, and Donaldson and Gromov and those people, and 40 years ago. But this kind of invariant is keep very interesting until now. So this is the 1980s. And then after a while, late 1980s, Andreas Floer came to this and his new feature of this Floer is the following thing. So in this Donaldson theory and the Gromov invariant or Gromov-Witte invariant, it is the counting of the numbers. So output is a number. But then Floer kind of do something a bit different. So he defined the groups. So in place of this counting the numbers, he defined groups using very similar kind of ideas using moduli space. So that's this the story of the Floer homology started. And I want to explain a bit more about the Floer homology. So in a Donaldson story on in a Donaldson story on this gauge theory, he counts the number of solutions of unsatisfactory equations on a 4 manifold. But then in the Floer story, he defines some group, so-called Floer homology, or in this case called instanton homology, on 3 manifold. So in the 4 manifold, this Donaldson invariant is a number, and in the 3 manifold, Floer homology is a group. That is this Floer somehow changes the story a bit. Actually, Cliff-Taubes defines some, so Cliff-Taubes gives something like a number for 3 manifold equals some number. That is actually equal to, found to be equal to this Casson invariant. So Taubes gave a number, but Floer kind of found that this number is something like Euler number of this Floer homology. So this is something like, this is a number, and this is something like group. So he somehow change the stories from number to groups. So that is the case of this gauge theory. And then in a world of the simplex geometry, Gromov gave a number of, so he got the numbers which are solution of the nonlinear Cauchy-Riemann equations. Actually, after Gromov, Yon-Bin-Wan made this very explicit that this kind of numbers to say that the analogy of Donaldson invariant in a holomorphic curve world. But anyway, so this is Gromov's work. And then Floer at the same time defined the groups for Floer homology. And in this Gromov and the Witten's invariant, they start this kind of map from sigma to x. And this sigma is a Riemann surface, but which has no boundary. And in this Floer's work, Floer use a map from disk, so this disk, it has a boundary, or this non-compact things. And the disk is used in the case of when there is a Lagrangian submanifold. And this R cross S1 is used to define Floer homology for some periodic Hamiltonian systems. So Donaldson and Gromov gave these numbers, and then Floer kind make it to groups. And so a bit more precisely, so if you consider this 3 manifold and the gauge theory, so he considered this some bundles, like this is bundles, mostly SU2 or SO3 bundles, and he considered flat connections on this 3 manifold. So you have this set of gauge equivalent class of flat connections. Typically, the set of flat connections on 3 manifold has a dimension 0. So typically, this set of flat connections that I want to write R of M, this is a finite set. So he considered this finite set, and he considered vector space, so whose basis is a set of flat connections. And then he considered this boundary operator. So you consider this Floer's chain complex, and it is a kind of, you consider this flat connections, and you take this maybe Z, and you have this boundary operator, and the boundary operator is some kind of count, and this one is he considers this M cross R, and one considers this ASD equations. And the number of the solutions of this equation gives this boundary operator. So that's an idea. And in a world of holomorphic curve, simplex geometry, so there are 2 cases, but I just want to consider this Lagrangian Floer homology. So Lagrangian Floer homology is the following things. So he considers this symplectic manifold. It is so they had a closed form on X, and this n power of this form is a volume form. It means that it never vanishes. And then he considers this Lagrangian submanifold. So it is the n-dimensional submanifold of this 2n-dimensional symplectic manifold. And the assumption is that symplectic form restricted to this Lagrangian submanifold is 0. Then he wants to consider this Floer homology of a pair of Lagrangian submanifold. And this Floer homology of the pair of Lagrangian submanifold is the following object. So the first one, he considers this chain complex, and the generator of this chain complex is a point of intersections. So this one is n-dimensional manifold. So typically, so the intersection is finitely many points. So this you have this finitely many elements here, and one consider the abelian group, free abelian group generated by this intersection point. So that is a vector space, and then one define boundary operator, and to define boundary operator, we consider this kind of configurations. So we consider these configurations. So you have this two things. This is L1 and this is L2, and we consider this intersection points. And then Floer considers a map from strip R cross 0, 1 to this to X. So this is in X to X, so that this part of the boundary go to Lagrangian submanifold, and the other part of the boundary go to the other part of the Lagrangian submanifold. And if you go further, this is tau t. When tau go to minus infinity, this go to p, and when tau go to plus infinity, this go to q. So you have this kind of boundary valued problems, and count the number, and then this is npq, and the definition of the boundary operator is this. So the boundary of p is just npq and q. So this is a boundary operator, and in a certain cases, Floer proves that the boundary is square. So Floer proves that this boundary square is 0, and that is a Lagrangian Floer homology. It is something like you just consider this intersections. It is the intersection numbers, and the intersection number is a number, but he get a group whose Euler number is an intersection number. So this is a Lagrangian Floer homology, and right after Floer found this Floer homology of three manifold, then Donaldson and Floer found an interesting relation between Donaldson invariant. Donaldson invariant, this is a kind of invariant of 4 manifold is just a number of ASD equations, solution of ASD equations. And then it's here. Maybe just so Donaldson found this interesting relation between Donaldson invariant and Floer homology. So you have a 4 manifold whose boundary is M3. So you have this M3 with this X. Then Donaldson invariant is so what the Donaldson and Floer found is that in the case when X has a boundary, Donaldson invariant is not a number, but is an element of the Floer homology which is a kind of this Floer homology is associated to this 3 manifold, which is the boundary of X. And this is a relative Donaldson invariant. And in a case when this, so you have this X1, and you have another X2, which is also a boundary M. So boundary of M, X1 is M, and the boundary of X2 is M. And the next is somehow group them. You get this X. And then the invariant of X, which is actually a number, is somehow you have this 2 element in this Floer homology of M. And Floer homology has some inner product, and you take this inner product of this, then you get this number. So that's a relation between Floer homology and the Donaldson invariant. And so this is somehow found this 80s. And what I want to emphasize say that in this case, Floer homology. So now something I want to say is the following things. So Floer homology is somehow you have this chain complex together with this boundary operator. And what's important in this case is that this chain complex itself is depends on the choices. So I mean, to define these ST equations, we need to fix star. This came from somehow like Riemannian metric. This is the extra choice. So we are working on this. We are working on differential topology, not differential geometry in this setting. So Riemannian metric and this Hodge star is some extra data. So the equation itself is depends on the Riemannian metric or conformal structures. However, what is very important in Floer homology is that this chain complex itself depends, but its homology group, or better to say chain homotopy type, is independent on the choices, and it's invariant. And so this is a bit more kind of complicated than Donaldson invariant, because Donaldson invariant you get a number, and by signed count, and this number itself is already well defined. But in a Floer homology, you see that this number appears. This kind of number appears in the definition of the boundary operator, and this boundary operator itself is not independent on the choices. So this Floer chain complex is not independent of the choices, but and as a whole, in the sense that this as a system of the numbers, up to some equivalence, is independent of the choices. And this is kind of the first time that this kind of homological algebra appeared in the story of this kind of topological field theory. Because kind of in a Donaldson invariant, what is well defined is rather simple. It's just a number. But in a Floer homology, so we need to do some kind of algebra before you get something really independent. And the story is going on. So if we go further to get more structures, and we get more and more sophisticated structures, that is happening after these players in this 30 or 40 years. And then in which sense the invariant we obtain is well defined, it's kind of more involved. So we need to do some homological algebra before we really understand what is the output of this full story. That somehow is a typical phenomenon on this Floer homology business in this 40 years. Okay. So now I talked about this Donaldson invariant and Floer homology. But as you see that I am oversimplified story a bit. And Donaldson invariant is actually not precisely a number. So you have a four manifold. Then what Donaldson said is a polynomial invariant. You have this some Q. And this you have this sigma I. It's just maybe typically two-dimensional homologic class. So Donaldson invariant is not simply a number, but it's a kind of polynomial defined in the homology group of X. It's a bit more complicated. And also, there are some more some parts which make story more complicated. So we consider this H2 of this four manifold. Then this has a pairing. You have an element alpha beta here, and you take this cup product and integrate. So this is a kind of symmetric inner product. And this B2 plus is a number of positive eigenvalue of this intersection pairing. And B2 minus is a number of negative eigenvalue of this intersection pairing. And Donaldson invariant is somehow, here this B2 plus is 0. Then Donaldson invariant is not well defined. And B2 plus is 1. Then there is something called a wall crossing and a chamber structure. And so the Donaldson invariant is not a number, but it's somehow number after some ambiguity. So there's topology. So it's not so much a kind of, so this story that give a number, the boundary gives this group is somewhat oversimplifications. And in a Floer homology, I didn't write so much imprecise, but there is also some cumbersome phenomenon, so that Floer defined only for this homology sphere. And also there are something called the trivial connections, which makes the story somewhat more complicated. And this phenomenon, in these cases, there are something complicated, and if you go to this B2 plus is 2, then there is a very defined number. This kind of thing is somewhat similar to this stable and unstable homotopy theory. As you know, that if you consider homotopy group of X after taking M suspensions and pi n plus m, and this Freudenthal theorem says that if M is sufficiently large, this group is independent on M. But for smaller m, there are some kind of some behavior which is hard to understand, but in a sense which is more interesting to understand. And a similar stability phenomenon in 4-manifold topology. If you consider 4-manifold and you take the connected sum of 4-manifold of some copy of S2 class S2, for example, then if m is kind of already 1 or 2, then this may be very small number. Differential topology on this 4-manifold became much simpler, or maybe not so interesting. And what interesting is the case when m is small. And so this is something like a stability phenomenon. And if you consider these cases, that if you consider this Donaldson invariant or gauge theory, then if B2 plus is 0 or B2 plus is 1, then this Donaldson invariant is kind of more complicated. However, this doesn't mean that if you consider ASD equation itself, and its moduli space, and actually in these two cases, the studying of the moduli space of this ASD equation is actually very powerful. And Donaldson proved some very important result about the intersection form of 4-manifold using ASD equations in these two cases, and the cases when it's B2 plus is small. And then that is something like an unstable phenomenon, and it is kind of harder to understand but interesting. And if you go up to this positive Betty number getting larger, then the story is getting somewhat simpler. You get well-defined invariant, and this topological field theory picture kind of getting simpler. But in a sense, what makes this story very interesting and non-trivial is probably the case of these unstable cases. So I think there is a kind of axiomatic study of topological field theory. I think Adair gave an axiom of topological field theory, so that you have a n-dimensional manifold, and then you have this some cobordisms, and you have this n-1 thing. This is a group, or something like that. And this story of this axiomatic story of topological field theory is now going on until recently. And this axiomatic topological field theory is interesting. I heard that something like even they are starting to try to apply it to physics. However, if you try to cook up this topological field theory from nonlinear PDE, like gauge theory, then what is very typical is that this axiom itself is not literally satisfied. It is satisfied only roughly. Kind of, there are some flavors so that axiom is satisfied, but there are something which makes story more complicated, and axiom is satisfied only kind of up to some ambiguity. And there are some unstable phenomenon which makes the story interesting, and probably what happened in this unstable phenomenon is the reason why that story is so deep and interesting. So yeah, so this Donaldson invariant and the Floer instant homology is a topological field theory picture late 1980s. Probably Witten introduced this notion of topological field theory, kind of inspired by this example. And so now I will go to the other kind of stories, Gromov-Witten invariant and Lagrangian Floer theory. So Gromov-Witten invariant, you have the symplectic manifold. Then this Gromov-Witten invariant is a number, or kind of number, but depending on this homology group of X, plus maybe something called that homology group of Drini-Mumford moduli space, kind of things. But this is a number, basically a number. And Lagrangian Floer theory, you have this two Lagrangian submanifold, you get homology group. And the Donaldson invariant and Floer's instant homology is somehow related, so that this invariant of X is an element of Floer homology of M. And there are similar, some relation between this Gromov-Witten invariant and Lagrangian Floer theory, but it's different from this Donaldson Floer story. And I will go back to that kind of thing later on. Okay. So now there are some story about the categorification of invariant that started in late 80s, 1980s, and it's continues up to now. And I think this first instance that this categorification started is this Graham-Ziegel. And Graham-Ziegel kind of studied these categorifications of conformal field theory in 1980s. And I want to explain it quite a bit. So the story in this group, Ziegel's story is Witten's three-manifold and not invariant. So what is this? So Witten considered a closed three-manifold X3, and together with a link. So link is some disjoint union of S1 contained in X3. And then Witten considered this Feynman path integral. He considered a set of all connections, on this three-manifold, and take this so-called Chern-Simon integral. It is something like trace of A EA plus A cube X3. And then he put some numbers. So this is kind of basically holonomy of connections along this link. And he takes these integrals. And of course, this is a kind of mathematically hard to define, but Witten managed to say that well-defined numbers. And this is a Witten invariant. So that associate number to three-manifold. And let me remind you that Donaldson invariant associate numbers to four-manifold. And Floer instanton homo. So this is dimension 4. Oops. This is dimension 4. This is dimension 3. And Witten invariant is dimension 3. And then there's what is the analog of Floer homology in dimension 2. And Witten gave an answer. The answer is this so-called conformal block associated to two-manifold. That is something like you have a two-manifold, then you consider the moduli of vector bundles on it, and there is some line bundle on the moduli of vector bundles, and the set of holomorphic sessions on this line bundle is called homological block. So this is the vector space. So Witten found that this relation to this two manifolds, and then Witten include this picture some notes. So you have this kind of, you have this two manifold, this three manifold, three manifold. There's a note and links give some kind of pictures like this. I have this two manifold with links. So then you get numbers, and this number Witten found is to be this Jones polynomial, and its generalizations for this not invariant. And this gives a kind of topological field theory descriptions of Jones polynomial. I think Witten himself talked about it in this series of lectures, so I don't want to talk so much about it. But so this is somehow, this one-dimensional less version of this Donaldson Floer pictures. And I think Graham-Ziegel give this categorification of this conformal field theory. So what is it? So the Witten invariant associate number to three manifolds, and the conformal field theory gives a vector space to two manifold. And then you have this one-dimensional manifold. Then Graham-Ziegel claims that there is a category, so that conformal field theory kind of reduced to this category theory in dimension 1. This category is somehow related to this loop group. Okay, so now this is Graham-Ziegel's proposal categorification of conformal field theory. Then this axiomatic study of topological field theory goes something like this. You have an n-dimensional manifold, then you get a number, like a Donaldson invariant. And you have n-1 dimensional manifold, then you have a vector space or a group. And when this x is m n-1, then this invariant is an element of this. So you have this z of x, this h of x n-1. This is an element of this h over m n-1. Then you have this codimension 2, you get a category. And then you have this kind of x boundary of m n-1, it's n, so this c over n. Then this invariant of this m n-1 is an object of this category. That is this category. And then you have this one-dimensional less, you get something called a two category. And then codimension k sig is a k category. So that is somehow general picture of the topological field theory. And this kind of study started in this 1990s. After this Witten's proposal of topological field theory, people go further to go higher codimensional things. I think when I first, when I was doing something a bit in gauge theory in early 1990s, many people talk about this topological field theory pictures and all these things. And then, so this is the topological field theory. So then how these things works in an explicit example, it came from gauge theory. So Donald's invariant on a 4 manifold is an invariant z of x, that's a number. And for 3 manifold, Floer associated some vector space that is a Floer homology, or better to say the group. And if you have a 4 manifold whose boundary is M, then you have this Donald's invariant relative to boundary, and that is the element of Floer homology group. And then in a 2 manifold, so you just go to this analogy of this what Graham Ziegler proposed. So we are supposed to get some category. And then if you have this 3 manifold whose boundary is 2 manifold, then this relative Floer homology is an object of this category you associate to this 2 manifold. So that should be this codimension 2. That should be this topological field theory, which came from gauge theory and anti-self dual or Yang-Mills equations. And actually in the year 1992, in a conference at the University of Warwick, Donaldson gave a talk and he proposed this, what is this? And so for this proposal, so we consider R of sigma, so you have this 2 manifold, and suppose you have some bundle, it is typically SU2 or SO3 bundle. Maybe we can try to generalize, but like this. Then we consider the modular space of flat connections on this 2 manifold. And Will Goldman found that this is a symplectic manifold. Basically, the tangent space of this R of sigma is somehow H1 of sigma with this twisted connections. And this symplectic form is just a cup product. So this is the symplectic structures. And so, so then the Donaldson proposal about this category is that this is a category whose object is a Lagrangian submanifold of this symplectic manifold, which is a flat connections. And then if you have a 3 manifold whose boundary is this 2 manifold, then we consider this R of M. So you have this M3, and this is sigma 2. And then this R of M is a modular space of flat connections on this 3 manifold. Then you can restrict the connections. So you have a map from R of M to R of sigma. And if you naively count the dimensions, then we found that this is a dimension of R of M is 1/2 of the dimension of R of sigma. And if you consider Stokes' theorem, we found that symplectic form, which is basically a cup product, symplectic form, a cup product vanishes here. So it is a Lagrangian submanifold. But it's not embedded, but it's a kind of immersed Lagrangian submanifold. But Donaldson's proposal is that this relative invariant, the object should be this particular case is this flat connection on 3 manifold. So that is what this Donaldson said in 1992. And then so you have this 2 object on this category that is a Lagrangian submanifold. And then you have to think about what is the morphism from L1 to L2. And Donaldson says that it's a Floer homology between these 2 Lagrangian submanifolds. So Lagrangian Floer homology. And then one need to have some composition of 2 morphisms. And then what Donaldson claims is that you count this triangle, which bounds this 3 unions. So this is a picture in this R of sigma. If the 3 Lagrangian submanifolds, then you count this holomorphic triangle, and that gives this map, and that should be the composition of morphisms. So that is somehow Donaldson proposed in 1992. And there is some background of this proposal that is called Atiyah-Floer conjecture. That the Atiyah-Floer conjecture is the following things. So we consider M3, and one take this Hegard decompositions. So you have this genus 2 Riemann surface, and this bounded, this is 100 body. You have another 100 body. And it is known that all three manifold is just decomposed into 200 body glued on this Riemann surface. And then there's Floer conjecture says that if you try to study this Floer homology of this closed three manifold, then you take this Lagrangian Floer homology. So remember that this R of sigma is a symplectic manifold. And this R of Hz and R of H prime Z is a Lagrangian submanifold on this symplectic manifold. Then we consider this Lagrangian Floer homology. Then Floer conjectures that these are equal. And this is called Floer conjectures. And this Donaldson's proposal in somehow so generalize this kind of Floer conjecture. The Floer conjecture is somehow, the three manifold its boundary is a 100 body. And he tried to think how to generalize this story of three manifold to general three manifold with boundaries. Then it goes to this Donaldson's proposal about this 3 and 2 dimensional topological field theory. And this is in 1992. And in those days, there are many attempts to solve this Floer conjecture. And I think those people wrote some papers. Dietmar Salomon, Yoshida, Lee and Lee, and blah, blah, blah. And one solid established result is due to Dostograf and Salomon. So they consider the case so that the space one consider is not a 100 body, but it's a Riemann surface group 0, 1. So this is a Riemann surface cross interval, and this is another Riemann surface cross interval. So you glue them together. So then you get this M3 that is somehow Riemann surface bundle over S1. And they consider this vector bundle on M3, so that if you restrict this to this Riemann surface, this is non-trivial. So this is SO3 bundles. And Dostograf Salomon basically proves something very like this in these particular cases. And there are more attempts to study this, the original case of 100 body. It seems likely to me that the problem, the Floer conjecture, is more difficult than people thought in early 1990s. In fact, 30 years later, it is not yet solved. And actually, even worse, it is not yet formulated rigorously. The issue is that this R of sigma in the situation of 100 body is singular. So usual Floer homology is not defined on a singular symplectic manifold. And how to understand this Floer homology in that singular situation is an issue, and which is I hope to understand it in the near future, but not yet rigorously. So this is not yet a rigorous conjecture 30 years after that. Okay, but then and at the same time, Donaldson tried to enhance this conjecture so that you get this full topological field theory in dimension 3 and 2. So this is a Donaldson proposal, but and at the same time, it seems that this, Donaldson actually in this talk, he said that this is not a so Lagrangian submanifold, or this is not this is something like a kind of fast approximations. So it means that this Donaldson's proposal is in principle correct, or kind of basically correct formalism, but it's not literally. So let me consider a very simple case. If you have a manifold, if this is S2, you have M. So now we consider this space of flat connections on S2. That is just a point. There is no flat connection, just like a trivial connections. So if you consider this map from flat connection on M to the flat connection of sigma, and the flat connection of M is of course equal to, you just kind of glue these three, so this is M plus. So you have this flat connection of M, and this map, and typically this is a closed three manifold. So this R of M is a finite set. You have a finite to one map, and of course, one point is a symplectic manifold. trivial symplectic form. And the finite to one map is a Lagrangian immersion. So this is a kind of special case of this picture. So what one means that this is a immersed submanifold of trivial symplectic manifold. And this is, remember, of course, a set of flat connections on this M plus. However, so you just consider this R of M itself, then you have only flat connections, and the boundary operator, which defines Floer homology of M plus, is not remembered. So the Lagrangian submanifold of this R of sigma, remember some part of this relative invariant, but probably one need more information to obtain this correct picture. So you want to make more precise and from Donaldson's first approximation to get the actual pictures. So to obtain this, so that is somehow clear in those days. So in those days, so kind of somehow that's the time I started working on this gauge theory type things, and so I was thinking about what is the correct pictures, and there are some so we know we need to understand this category theory, and one important theorem is so-called Yoneda's lemma in category theory. So Yoneda's lemma is very easy to prove, but it's a kind of important integrand. You have this category, any category, and you consider the set of all functors from opposite category. Opposite category has the same object, and just the arrow is opposite. And you consider the functor from this opposite category to the category of all sets. And you have these two categories. The set of all functor is a kind of another category, actually two categories. And Yoneda embedding is a kind of functor from C to C up to set. And we have a C that's an object of category C. They have a C prime and object of C op. Then you consider this morphism in the category C. So that's a set. So this C prime go to C, C prime C. That is a functor from C op to the category of sets. And so this is a Yoneda embedding. And Yoneda's lemma says that this is an embedding of categories. And this functor has a kind of very important meaning. And you have the moduli problem and representing the moduli problem is something like representing the functors and this Yoneda embedding. But what this Yoneda embedding means? So it means that this functor from C up to set is a kind of enhancement of an object of C. So you want to get more object than C, the object of C, you consider this functor. And in the kind of there is analogy, so you consider Yoneda embedding, it's something like a categorification of the following well-known things. You have a smooth map on manifold, then you get a distribution like a current, and then so this is by duality. So this is some kind of a duality. So this embedding is in a sense very similar to this Yoneda embedding. So you want to generalize smooth function to distributions. It's somewhat similar to this using Yoneda things. So something I just conjectured in 1993 is that you have a three manifold is boundary sigma, then this relative invariant is not the object itself, but it's a functor from this thing to something. So what is this something? So this morphism on this category is a group that's a Floer homology or a chain complex, which defines Floer homology. So you want to define Yoneda embedding on this category. Then it is slightly different from this original Yoneda thing. It's just here it's called sets, but it's Yoneda embedding is the following. So you have a category, and then you consider this category to this chain. So chain is a category of chain complex, and you have this natural embedding. So this is some kind of version of Yoneda embedding. So the conjecture is that this relative invariant is a functor from this category of Lagrangian submanifold to the category of chain complex. So let me remind you that this category is, but I think this Yoneda embedding is a bit more involved. So you want to prove this Yoneda lemma and kind of proper correct story on this Yoneda embedding. Then we need to kind of enhance, modify this the Donaldson definition a bit. So the space of morphism is not, we just change it to that's the Floer homology group, but I want to modify it to the space homomorphism is a chain complex, which define Floer homology. But then I consider the composition of homomorphism, this triangle count, and actually in a level of homology group, this composition of homomorphism is exactly associative, but if it goes to the chain level, then this composition is associative only up to homotopy. And you can go on. Then there is a notion by A infinity category. So this Jim Starchev defines a notion of A infinity algebra. He studied this loop space and loop space homology, and he found that there is something called A infinity algebras. And the algebra, the notion of A infinity category is also known along that time by this topology people. But then this Lagrangian thing exactly give this A infinity category. That's an observations. And also, you just enhance this category so that this infinity versions, then you have proper Yoneda embedding. So the conjecture is following things. So we can associate this infinity category to a symplectic manifold Y. And you consider the case when this Y is a space of flat connections of two manifold. And then this Floer homology is an infinity functor from this infinity category associated to these flat connections to the category of chain complex. And this kind of infinity functor is called actually recently more called infinity module in the case when this is particular chain. So I want to, so this is the kind of abstract way of thinking. But then let me say what is a more kind of down to earth way to say that this infinity functor. So what is this infinity functor? So it associates, you have an object here. It is a Lagrangian submanifold. So you have a Lagrangian submanifold of this space of flat connections. Then you are supposed to get a chain complex. So you get this this chain complex, and then how we get this chain complex? So let me remind you that this usual Floer homology, we consider this, you have M boundary is empty. Then the main part of the definition of Floer homology, we consider this M cross R. And we study these equations on this four manifold, which has an end but no boundary. But then in our stations, you have manifold M as a boundary. So you consider this M cross R. They have this right. So here this M cross R. Then this has ends when this tau go to plus infinity, but also boundary. So I want to study this ST equations on this four manifold, which has both ends and the boundary. And then on an end, you get some flat connections to put asymptotic boundary conditions. But on these boundaries, you need some boundary conditions to have a proper Floer-Holm theory and to get the good moduli spaces. And the idea is that this L, which is a Lagrangian submanifold on the space of flat connections, gives an a way to put boundary conditions on this on boundary of this four manifold M cross R. So that's an idea to get this infinity functors. But then so that is something like I was thinking on this 1994-5, and actually defining boundary valid problem on this four manifold is actually a very difficult analytic problem. You can imagine you have a four manifold which has a boundary and end, and on the boundary you have some very much moving boundary conditions, and this L, and it is something like a half infinity type boundary valued problems, which is something like a non-linear version of a Zinger type. And I was trying to correctly formulate this boundary valued problem in 1999, this mid-1990s, to get this infinity functors or infinity modules. But my research those days was not successful yet, kind of conjectures, but not yet written completely. And then there are some reasons that I just left it. And then in the early first half of 2000, Dietmar Salomon and Catherine Wilhelm finally cook up to some correct formulation of this boundary valid problem to find this Floer homology group. So in a situation, you have this three manifold M, whose boundary is sigma, and L is given as a some Lagrangian submanifold out of sigma in certain situations. Then they define some chain complex and homology group. So that is what they call Floer homology group of M with Lagrangian boundary conditions. So they gave this, so they have this correspondence L to this HF ML. So that is something like object part of the functors we want to understand. However, their construction is not yet functorial. This means that the morphism part of this functor is not yet defined. And then time passed. In a Hegardt Floer homology, that is minus something which should be Seiberg-Witten Floer theory, but Osbach Sabo did it so that they can do it without minimal use of nonlinear PDE, more topological and combinatorials. And then in their work, Lipschitz, Osbach, and Thurston define infinity module associated to this three manifold with boundary, and sigma they get some DGE, and this they get infinity module. So that's very similar to the pictures which we could not do in Jan-Mills theory in 1990s or 2000. And I think, but this research is not yet completed. But this Simon Hegardt Floer world, things are go probably because Seiberg-Witten theory and the Hegardt Floer theory is kind of get more computables and kind of more easier to work with. So they take this advantage to go ahead. But now I'm trying to study with this Algebra Daimi and Max Lipinski, try to find this in a functorial way, starting to 2070s and still working on it. Okay, so let me go back to this infinity category. That's a concept which called Fukaya category, and the issue how to understand it. And actually, this category is in concept, which is a famous proposal of homological mirror symmetry. He used this category. He used this category, but that's a kind of different story from what I'm talking. But something I want to say is that, as I said, that in a topological field theory pictures, usually this kind of topological field theory in a geometric realization is somewhat not simple. There are some complicated things which makes things difficult. And in a Lagrangian Floer theory case, is probably mostly complicated case. So first Floer invented Floer homology. So he in his case is a very simple case. You have T of M, you have Lagrangian submanifold, which is somehow a very simple thing. So that pi 2 is the M is 0. In those cases, what Floer defines that you have two Lagrangian submanifold, then you have a Floer homology well defined, and the rank of this Floer homology group is smaller the geometric number of intersections. And there are invariants of the Floer homology, so-called Hamiltonian deformation. That makes Floer homology interesting in symplectic topology. Hamiltonian deformation is something like a time one map of Hamiltonian vector field. You have two different time one map, then this Floer homology is invariant. And finally, one can calculate it. If two submanifold is the same as some manifold itself, the Floer homology is the homology of L itself. So this is what Floer proved in this particular cases in 80s. And people try to generalize this Floer theory so that it works in more general and using O, generalize in some cases so-called monotone cases. And we are trying to generalize it. However, actually, this is again oversimplifications. And in general, this full set of package is not true. So the very simple case is the following things. If you consider this, sorry, this is R2M. It's 2n dimensional symplectic manifold, R2M, Cm, and you have two compact Lagrangian submanifold. Then suppose that we assume that 1, 2, 3 is correct. Then actually there is some Hamiltonian phi, so that phi L1 and L2 is empty. So this then this 2 and 3 implies that this Floer homology is 0, but 4 says that this is equal to homology group. So this never correct. So in a very basic case of C2M, then there is no such a theory. And also, even if this 1, 2, 3 is true, Floer homology is actually 0. So it seems very likely that Floer homology is trivial at 2n. I recall that in a case of Donald's invariant, B2 plus is 0, then Donald's invariant is not defined. And in a very basic case of R2n, Floer homology of Lagrangian submanifold is not defined. But however, we know that in this particular cases, moduli space of ASD connections is very useful to four-dimensional topology. Donaldson classified that H2 of X is just this trivial intersection form in this case, and this is based on this. So Donaldson invariant is very ill-defined, but the ASD connection is very powerful. In a similar way, in a sense that in an R2n, Floer homology is always 0. But you can use the fact that Floer homology is 0 to understand something. One typical thing is that this Ilie classified irreducible three-manifold, which is a Lagrangian submanifold of R6, using this kind of Floer type business. So Floer theory, kind of pseudo-homological curve is powerful in R2n, but the story of Floer homology is not such simple. So kind of in 10 years between this, maybe 15 years after this middle 1990s and 2010, with Ono, I'm working on this Lagrangian Floer theory and try to find the correct stories on this Lagrangian Floer homology. So our conclusion is the following things. So the Floer's kind of, this most naive guess is that you have two Lagrangian submanifold in symplectic manifold. Floer homology is defined, well defined. That's not so much true. The correct story here about Lagrangian submanifold in symplectic manifold, they have some space, which is a subspace of space of odd dimensional cohomology, so that if you have an element Bi on a Li on this space, then the Floer homology is defined. And this space can be empty. So what we found is that Floer homology, in that case, of course, Floer homology is never defined. So in this case, Floer homology may or may not be defined, and also you have extra parameter to have a well-defined Floer homology. And another thing is part 4, in this naive picture, if you have this Lagrangian submanifold, which is L1 and L2, and then the naive expectation is the Floer homology is equal to ordinal homology. But what actually is, there is a spectral sequence which goes from ordinal homology to Floer homology. So Floer homology is something like a bit can be smaller than this homology group. For example, you have L in Cn, then the H of L is non-zero, but most likely Floer homology is 0. Okay, so this is a kind of stories. So what we found is that it has an extra parameter, so that's called the bounding constraints. And actually, to find this kind of stories, we need a lot of homological algebra. Basically, it is a deformation theory of associative algebra. And you have this kind of maybe DGA. This is DGA. Then we have this deformation theories. And this infinite algebra, the deformation theories, there are homological algebra, homotopical algebra, which controls the deformation theory of the graded algebras. That homological algebra we use to obtain this Molar-Cartan moduli space and the so-called bounding constraints. And then Akaho and Joyce came. This is late 2000. And then they generalized the story from embedded Lagrangian submanifold to immersed Lagrangian submanifold. The new feature they found is that this deformation space is not just this odd dimensional cohomology, but you have two extra generator for each self-intersection point. For example, you have this kind of thing. So S1 with self-intersection. So that this one is somehow H1 S1, but you have this 1 point plus rank 2. So this is a deformation space. Okay, so now this is kind of Lagrangian Floer theory in a kind of, now this kind of, after 15 and 20 years, we have this picture. Okay, so now, yeah, I think I talk this kind of stories. The first reaction is, oh, story is very complicated and kind of not well defined. So I'm not so much happy. But actually, something we found is something like 2009. Is that this extra parameter make this Floer theory is kind of more applicable. I just want to say one very simple example is the following things. If you consider CP2, two-dimensional projective spaces, and this is a toric manifold of T2 actions, and I want to consider this Floer homology of L. L is a T2 orbit. And it is known that this Floer homology actually is 0 almost always, but it's non-zero for some particular L that is called a Clifford tori. So Floer theory is somewhat non-trivial for this particular L. Then we blow up. So your manifold is CP2, connected sum of minus CP2. And this is again toric, T2 actonic. So we consider this torus orbit, and we try to calculate Floer homology in the usual Floer sense. And then this Floer homology is 0 always. So in some sense, this Floer homology is more trivial. However, if we include this extra parameter B, then we have exactly 2 Lagrangian submanifold, which is T2 orbit, so that Floer homology is non-zero. So if you want to kind of apply Floer homology, for example, something called a Lagrangian intersection or symplectic rigidity, then this ordinal Floer homology is not enough powerful in these cases. But if you include this extra parameter, it is enough powerful. So that's the stories. But this is more purely Lagrangian case. And also this parameter is useful in mirror symmetry, but that's another part of the stories. Okay, so now after this 20 years, something like at the stage of 2017, we have this Lagrangian Floer theory, which is a two-factor. What is it? It's a two-factor from this category of all compact symplectic manifolds, and we consider the category of two categories of all empty categories. So this is a kind of, we just started this object part of this functors, and Akaho joyously enhanced it to include immersed Lagrangians, and Wilhelm Woodward and Moe started to study about this morphism part of this functor, and in 2017, so they showed this functors under certain restrictions, and I finally removed those assumptions. Now we have these two functors. And I want to say a bit more. So what is this? So you have this category of all compact symplectic manifold. And what is the morphism from M1 to M2? The morphism is a pair LB, and L is a Lagrangian submanifold. So this is Lagrangian submanifold of direct product by M1 and M2, and B is something called this extra parameter which defines Floer homology. It is Weinstein to regard this kind of L as a morphism in a category of Lagrangian submanifold, and this is called Lagrangian correspondence. And enhancing this particular parameters, we get this category, or better to say two category of all symplectic manifold. And then we have this functors. So this is something very similar to homology theory. So you have this category of spaces, and they have category of algebras, and you have this well-defined functors. And this picture is very much functorial. And actually, two categories of all infinity categories are rather kind of complicated objects even to define. And there are some homological algebra business just to define these two categories. And of course, if you want to define these two functors, you can imagine two functor involve so many operations. Okay, so now let me go back to gauge theory. So we consider this case of three manifold with boundary, two manifold. And then what I said before is that you consider this relative invariant. So you have this R of M, which is a mass Lagrange of R of sigma. And what I said before is that this guy does not have enough informations. We need more information than Lagrangian submanifold itself. And actually, after this 20 years, what we found is that this extra information we need is exactly this bounding cochain. So I want to explain this in a very simple example. This appears in this Bram and Donaldson's work in this Floer's memorial volume. If you consider this three manifold, whose boundary is just a disjoint union of T2. So you have this T2. And we put some SO3 boundary so that it is non-trivial on HT2. Then we consider this space of flat connection on T2 with this non-trivial SO3 connections. This is just a 1 point. There is unique reducible connections. And we consider this R of M to R of T2 cross T2. And again, this is the finite to one map. So this out of M is a immersed Lagrangian submanifold on this trivial simplex manifold. But then you have this bounding cochain. So this is kind of finite to one map. So self-intersection numbers, you have this kind of P and Q out of M. Then Akaho-Joyce generator is something like MPQ. It's a kind of this is something like a associated number to self-intersections. So it means that you have two flat connections, you get a number. So this is a B in our case. And actually this B in our case is exactly the boundary operator of instanton Floer homology. So you have this thing, so you just compactify it by taking this T2 cross 0, 1. You have this closed manifold. And then you have this instanton Floer homology, and the main player is just this number, that's the boundary operator. And that is exactly this bounding cochain. So in this very trivial example, so that simplex manifold is a point. Your bounding cochain is just this Floer's boundary operator. And in the case of this simplex manifold is non-trivial, you have some mixture of Lagrangian submanifold. Some information coming from Lagrangian submanifold and some information coming from gauge theory. And that information coming from gauge theory is this bounding cochain itself. And a few words about this formulation to use this MVT module is the following things. So you have this M whose boundary is sigma. Then we consider this. So then we have this MVT module that is this functor from this category to chain complex. But then I want to enhance this original category so that it includes not only embedded but also immersed Lagrangian submanifold. Then actually this functor is representable. It is an image of Yoneda embedding of this particular Lagrangian submanifold together with its bounding cochains. Okay, so now this is the pictures, and I believe that we can rigorously cook up these pictures and to construct this 2 and 3-dimensional topological field theory in a case when this out of sigma is smooth, and that is something I'm working on with Alkabadami and Lipinski, but it's not yet completed. We are now on the way of writing. So now I want to go back to the questions. How does transinvariant and Floer homology in the topological field pictures? Since I don't have a time now, I want to skip this part. And since I want to say about something about the moduli space, so I want to skip this part. And I want to say about some foundations. So the foundation is the things. So the foundation of all these stories, which I talked so far, is based on a study of the various moduli space of partial differential equations and self-dual equations or this pseudo holomorphic curve equations. And physicist interpretation is the following things, right? So we consider this Feynman path integral, the configuration space is infinite dimensional. So we just consider this space of solutions on this PDE, that is a critical point set of f of A. So you reduce this to finite dimensional integrals. But the problem is this finite dimensional integral is that this M, that's the moduli space of the solution of a nonlinear PDE, can be very singular. That are transpositive problems. And in our stories, this is a kind of integration on a singular space. But there are something worse. This number itself, in our story, those number itself is not well defined, but only some complicated system of such numbers are well defined in certain complicated sense. That's how this homological algebra means. So we want to justify this number integration over some singular space, but actually this is not completely well defined, but it's well defined only in a very complicated sense. So the approach to justify these numbers in a classical approach is the following things. We perturb the moduli space in a sense to get some explicit geometric parameter. And in the case of Yang-Mills theory, this theorem by Uhlenbeck means that the perturbing metric in a generic sense is enough. And in the story of this Gromov-Witten theories, in certain assumptions like semi-positivity, we perturb almost complex structure and you get enough. We get enough enough parameters. But in our story, yeah, but in our stories, so that the problem became more and more cumbersome. It means that we need to cook up so many numbers and so many relations between them, and it's a ill-defined, very definedness is getting more and more cumbersome. So we need to some more sophisticated tool to make this number well defined. And that is so-called virtual technique, which invented in around the year 1996. And we, myself and Ono, and Gantian, Li Liu, and Luan and Zibelt working on this years. And the kind 20 years, we have more and more advanced on this technique. The idea is the following things. So this M is a singular spaces, and we define some notion of singular spaces. And I want to say this is in symphytic category. It means that the space is, in algebraic geometry, we have the scheme, but we are in a symphytic category. And then we prove that the space is an example of this notion of singular spaces. And we develop certain cohomology theory in this singular space and justify these integrations. That is called a virtual technique. And nowadays, there are 4 variants of the virtual techniques. And one is this Kranich structures, which I'm developing with Ota Ono. And the other is the D-manifold, which is developed by Dominic Joyce. And there's a polyfold theory developed by Hofer with his collaborator, Wiskowski, Zender, and recently Fish. And there is something called the implicit atlas, which is developed by Pardon. And there are, I believe they achieve the same goal. And our story is something like try to generalize manifold theory in these singular spaces. And Dominic Joyce's story is somewhat very similar to what this algebraic geometry people do in the schema and stack. And they find some symphytic analog and some derived analog. And Helmut Hofer worked more on this functional analysis. The issue is that when the space we define nonlinear equations gets singular, then you cannot work on a single function spaces. You have some kind of function spaces when a domain changes, and they cook up some enhanced functional analysis so that it includes this kind of changes. And what Pardon did, Pardon just takes this kind of Kranich structure, very similar thing. But what is typical in Pardon approach is he don't want to do so much geometry on this kind of singular spaces. He immediately go from this singular spaces to some algebraic object and do most of the story to algebraic world, so algebraic topologies. And this technique, it is becoming clear that you work on this Gromov-Witten Floer world seems to work to realize this in a complete generality. And yeah, but then how about gauge theory? So we have these 2 types of stories. One is this holomorphic and gauge theory. And this kind of very complicated homological algebra, we can manage to work in a kind of, in a case of this holomorphic curve using this very sophisticated techniques. However, in a world of gauge theory, what is difficult is that the moduli space is more singular than holomorphic curve in the gauge theory. So the typical example is the following things. So you consider MDX. It's a compactified moduli space of AC connections. And what we know is that there is this particular point, so that you have this XX, then you have this D bubbles. You have this D bubbles. So all the mass on this instant on just bubbled off. So what is remain just 0 connections. And there are this particular point. And he looks at some interesting works by Donaldson to study this intersection forms. And the study of this particular configuration is very much important in his study. But this is very much a singular point. And I am pretty sure that this point, neighborhood of this point do not have a Kranich structures. So the formalism which developed in this virtual technique is not enough for gauge theory. So there is still some difficulty. So my final word is that what I'm doing in this diamond in this. So I don't remember. I'm supposed to talk until 10:30 or 10:20 and 10 minutes discussion sections.
Well, would be nice to have some discussion, I think.
Okay, yeah. So this is the last slide. That's good. Yeah. So what I'm doing this diamond is just in this particular case when this insertion is just 1, and the modular space is dimension 0. Probably we can work out virtual technique in gauge theory. But in more complicated situations, it seems harder. And I hope that we can do this kind of things in next 10 years, but not now. Okay, I stop here. Thank you very much.
Thank you.
So let's virtually thank Kenji for a wonderful survey. There are several minutes now for questions. If anyone would like to pop something into the Q&A. I was wondering if just way back in the history, whether Floer himself must have formulated or at least thought of the Floer conjecture. I just kind of wonder what the genesis of that idea was from presumably back in the 80s.
I mean, about this Floer conjecture?
Yeah.
I don't know. There is a reference Atiyah wrote about Floer conjecture.
Sure.
And I don't know how much Floer wrote about it. But I think what Floer wrote about this Floer's then triangle, Serge triangle, is some more enhanced version of this Floer conjecture. It's a relative Floer homology. And also, I think his last paper is something about the axiomatic characterization of Floer homology and something like kind of this kind of, this, if you include this Floer conjecture on this dense Serge triangles to generalize something, and if this all stories about the reducible is gone, then kind of you get the Floer type axiomatic characterization of this Floer homology. That I think is very much kind of related to this idea of topological field theory, maybe predated by many other works. And what's the difficulty in this instanton Floer homology, as you know very well, is more difficult than Seiberg-Witten Floer theory. There are some difficult parts that is not defined. So by this reason, this Floer's idea in using this knot theory is not kind of rigorously established. And so if one goes that kind of directions, probably this kind of topological field theory ideas. And probably Floer knows much more than he wrote. Yeah. He brings something to everyone.
A question now in the Q&A. Question is, can you explain briefly the part that you skipped before explaining the virtual technique part?
Something I wanted to say the following things. Just one word. Thank you for asking this. So yeah. So we can just say the one word is the following things. There is some map called open.
Kenji, we can't see you need to share your screen again.
Oh, I see. Yeah. So there is something called a closed open map, which comes from this quantum cohomology to the Hochschild homology of the category I've just discussed. And this is defined by this Kontsevich, Seider, Alberts, and Bilan-Cornelius and ourselves. And this map is known to ring homomorphism. So this gives some relations, at least. This f of x. So this is a category. This came from Lagrangian Floer theory, and you take the Hochschild cohomology. It's a ring. And you want to understand this Gromov-Witten invariant, and there's a kind of one of the first part is this Hochschild cohomology, and this Q is a ring homomorphism. And it is expected to be an isomorphism in many cases. So So this recover this homotopical invariant from Lagrangian Floer theory. And there are many works done in this direction, kind of how this category knows about the homotopical theory. It is related to this mirror symmetry.
Another question there popped up in the Q&A. How does Seiberg-Witten Floer homology relate to this story?
Yeah, actually, so this Heyman Floer theory and Bodel Floer theory should kind of go ahead because they probably define the same infinity modules. And yeah, unfortunately, I'm sorry to say that I don't learn Heyman Floer theory enough deeply to understand how much it is done. And in a world of this kind of Seiberg-Witten Floer theory, that then I think Seiberg-Witten Floer theory with boundary is studied by various people, but probably not yet in this completely in this setting. I think the problem is if you consider this three manifold, the space of flat connection is kind of rather topologically easy to understand. The solution set of Seiberg-Witten equation on three manifold is of course good invariant, but it depends on the metrics, and it's a bit more cumbersome in the three-dimensional case. And in relative versions, I don't know how much. There are some work I think to study this boundary valid problems, but not beyond that, I think. So there are attempts, but not yet completed. But I think the second Floer theory business is morally is a Seiberg-Witten version.
Two more questions just there. One is for the modular space of ASD connections, do you mean all the techniques you mentioned, FOO, Joyce, Hofer, L, Pardon, they fail to describe the singularities, or are you referring to the modular space of connections on a full manifold with boundary?
There are two points. So if full manifold with boundaries, without a boundary, then there are problem about the singularities. So there's no no current structures, and maybe polyfold theory, the analysis is still difficult to work out in this in the settings. And in a border case, there are still another difficulty. That's basically come from the singularity of space of flat connections. That's somewhat related, but it's slightly different. And there are many other questions we need to understand. So I don't know. And if you consider this algebraic geometry world, then the modular space of vector bundles, there are something like more works like Giesecke compactification. That has a better property than Uhlenbeck compactifications. But in a real world, compactification is more difficult. So people still, I think, on the way understanding the singularities.
And perhaps time for one last question, briefly from Jim Stashev. Do you have a reference for the Pardon approach?
I think Pardon wrote two papers. One is on this geometry and topology, and the other is about so the paper on geometry and topology defined this from Witte invariant and Hamiltonian Floer homology using this his approach. And there's another paper from Journal of AMS which gives this contact homology, some part of contact homology by the same approach.
Wonderful. So Kenji, thank you once again for a great talk. Been great to see you here virtually in my case in Massachusetts. And perhaps again we can all send our virtual thanks and applause to Kenji for excellent excellent talk.
Yeah, maybe we have to meet not virtually, right?
Okay. Okay, thanks. Bye-bye.
Yeah, thank you. Bye-bye.